Come on. I don't know why. Okay, half-life is how long it takes for half of whatever I had to start with to remain. It's easier, cut something in half rather than a third or a fourth or a fifth. Well, if it's a whole life, then that means it's totally gone. Okay, we never get really to a whole life. So half-life is the time it takes for half of the sample to decompose, whatever I had. So you should be working with your notes and following me through. The rate of nuclear transformation depends on the reactant concentration. Now, sometimes instead of concentration, we use activity because we use Geiger counters to count the activity. So we can say there's this many counts before, this is the activity after, and we can figure out the half-life. How many have seen this kind of graph in math before? Okay, what kind of graph is this called? It's called what? Okay. It's half a parabola. Okay. It's also known as a exponential decay. So this is an exponential decay. So if I took 20 grams to start with, then a half-life would be 10. Another half-life of that would be 5. Another half-life would be 2.5. Another half-life would be 1 point, as it goes down. So I just cut it in half every time. Now, as we do this, we have some equations that we need to deal with. So remember I told you that A could count for concentration. It could also count for a count, so activity. So as you're writing in your notes, make sure you get this down because you're going to need to use these equations. Okay, the ones in black over here sort of identify what's going on with the black equation, the ones in blue with the blue equation. You use a sort of combination of both of these. So if I know the initial amount and I know how many half-life it's going to undergo, then I can tell how much I'm going to have after that amount of time. But if I don't know the half-life, but I do know the total time and the amount of time it takes for a half-life, I can find out how many half-lives it undergoes. Okay, I'll give you a second to write this down. Pretty straightforward equations. They should be starting on the top or close to the top of that second page, I think, right by your nuclear power plant. Okay. We good to go ahead? A little bit more time? Okay. Yes. It's 2 to the n power. It's 2 to the n power. Doesn't show it real great, but it is 2 to the n power. Okay, so how do we detect radiation? Well, if you ever watched Ghostbusters, they had a thing that looked like this. It's a Geiger counter. And they'd hold it out and try and find the ghosts. It actually detects radiation. That's one type. We also have Skillion monitors, which are sort of like that, but they don't have the thing that you can hold out. They're just a monitor. And we also have radiation badges that if you're in the hospital, you wear a radiation badge to track how much radiation you've been exposed to. Okay, now if we had radium that we were working with, and it has a half-life of 3.6 days, and I start with 50 grams, how much is going to be left after one half-life? How much is one half-life? 3.6 days, right? So after 3.6 days, I'm going to end up with 25 grams. What happens after 7.2 days? Okay, good. I'll be cut in half again. What happens after 10.8 days? Okay, and if I went another 3, it would be half of that. So every time I go another half-life, I just cut it in half. Okay, pretty easy. So here's a learning check. Think of this before you do it. Okay, the half-life of I-23 is 13 hours. So that's how long it takes for it to cut in half. How much of 64 milligram sample, so that's what I start with, the sample of I-123 is left after 39 hours. So what's the first thing I need to figure out? How many half-lives? So how can I find out how many half-lives? Good. 39 divided by 13, which we should all be able to do in our head, which is 3. So I'm going to cut it in half 3 times. So 64 divided by 2 is what? 32. Divided by 2 again. 16. Divided by 2 again. 8. So I've got 8 left over. Okay? So that's a half-life. All right, so we found out how many half-lives. Then we just took, and when we did that every time, that's where we get the 2 to the n power. So 2 to the 3rd power would be 8. So I take 64 divided by 8, and I get 8. So instead of doing that every single time, because it's not going to end up real pretty all the time. It's not going to be 3 half-lives. It might be 2.7. And how do you know 2.7 unless you put it into a formula like this? Okay? All right. So we need to talk a little bit about the effects of radiation. Now, your doctor often worries about how many x-rays you've had. If you've had too many x-rays, he says, well, we're going to wait a little while, and then you will do the x-rays. The reason why is if we have 0 to 25 rems, no observed effect. Okay, nothing happens. But if we go up to 26 through 50, we've got a little bit of a white cell decrease. So what? What does white cells do? Protects you from disease. That's a problem. So I don't have as many white cells to protect me from diseases. Okay, then I go up to 51 to 30. Here I get a significant decrease in white blood cell count, and I get lesions. What are lesions?
Something to do with skin.
Sores all over your skin. Okay, big open sores. Okay, that's not so great, and I'm more prone to being sick, right? Then we get to the next one, 101 to 200, loss of hair and nausea. Wait a minute, that sounds like cancer, radiation treatments. This is what they do. They get the radiation treatments right here. They're trying to kill off the cells. Yes?
Wait, so this is like after one x-ray?
This would be, no, this is just what happens when we get so much radiation in our system. It wouldn't be just one x-ray. We'll talk about one x-ray in a minute, but this is a lot. Okay, a lot of radiation. What they do with chemotherapy and with radiation with cancer is they get you into this area right here where you lose your hair and you've got nausea, and they're killing off cells. Most people that have cancer can't be around other people. Why? Not only the radiation, but they can get sick really, really easy. And so they have clean rooms. They have to have somebody come in and clean the room and have it really clean. If they go past this and get up into the 201 to 500, this is where you get hemorrhaging, ulcers, death in 50% of the population. This is what happened at Hiroshima. Okay, as they got out, they had too much. And then you get above 500. That's what happened when the pilots flew over Chernobyl. They got this big dose all at once. By the time they landed, not much they could do. They were really sick and died. So let's look at what it all is. Now those were rem. This is millirem. Milli means what? 1,000. So just teeny, teeny amounts. So cosmic radiation, we're going to get 50 just because we're in the cosmos. On the Earth, just because we're on the Earth, we're going to get 47. If we go into buildings, which we do, we're going to get 3. If we inhale the air, which we do, we're going to get 5. The Salt Lake Temple actually is made of granite and is very radioactive, which is sort of funny. If you bring anything back from Mexico and it's painted in the red paint, that is usually very radioactive. The red, like they make their dishes that are red, you bring any of those back, those are very radioactive. That just the dirt that they make it with. Depends. We've had some that have gone clear off the scale. So, okay, so elements found in nature in our human tissue. We eat salt all the time. There's radioactive iodine in our salt that we eat all the time. So we're going to have some in our tissue anyway. 21. Subtotal, we get millirem about 126, which in rem is what? 0.126. Not very much. So here's some other sources. If we have a diagnostic x-ray, we're going to get 50, which is 0.05. Not a lot. Radiotherapy, this is more the higher dose therapy, is 10. Internal diagnostics, like if they're doing, looking at your thyroid or looking at kidneys or looking at your bowel system, then you're going to probably get about 1. Subtotal about 61. Okay? Other artificial sources, nuclear power plant, 0.85. 0.85. Nothing on this scale right here is less than that. It's very, very small. The only problem is if there's a disaster, and that's when Chernobyl or Fukushima or 3 Mile Island, which gave you a diagnostic x-ray, you get a little bit more. Luminous dials and watches, TV tubes, fallout from nuclear tests. Now that for us is really big because they did a whole bunch of testing in the West Desert, and we're still feeling the effects of that. Okay? So some things that we can use to detect them. This is your Geiger counter, and the Geiger counter has a handheld thing that's sort of off to the side, and you can just sort of go around. Most Cillian monitors, which is what this is, don't have the trigger gun. It's usually just a monitor that just sort of sits and it's just there. And you just, so if they're worried about radiation like at Chernobyl 5 miles out, they'll set a Cillian monitor rather than a Geiger. Okay? Film badges is what medical uses. There's several different kinds. A lot of them will turn colors. If it's red, then you're off without pay for a few days. If it's one like this that it just goes black if you've been exposed too much. Okay. So radiocarbon dating. This is how we find out how old things are in archaeology. We use carbon-14. How does that work? Well, in the upper atmosphere, we get this happening, which is nitrogen-14 and a neutron, and it gives us carbon-14. And carbon-14 then is changed into CO2, which circulates through the atmosphere, and plants breathe it in, we breathe it in. And as long as we're living and the plants are living, we're exchanging the C14 pretty well, pretty often. Okay? But when a plant dies, the C14 is not replenished. And so we're able to see a living plant next to something that's died and determine how far away from each other they are. Okay? It continues to decay. The half-life is 5730 years, so 5,730 years. That's a long time. So carbon-14 dating only works for things that have been dead a long time. Doesn't work too well for things that haven't been dead very long. We have to use other things. We use the activity of the sample. So we either use a Geiger counter or a Cillian monitor to see how much radiation they're giving off. Okay? This is a study where they did a study of the thyroid. So you intake some radioactive isotope, and a healthy thyroid gland looks like this as they're imaging. Now they put colors to different amounts or activities that come off of it, so it's easier to interpret rather than just seeing white and sort of white and sort of white kind of thing and black. Right here we've got one that shows hyperthyroidism where the thyroids are working way too much. Now the thyroids are right here in your throat, okay, look like a butterfly. So they can also detect cancers and stuff like that by how it's absorbed. We talked about last time foods and irradiating foods. If they irradiate foods, it kills the bacteria on the outside, and so they're able to transport it without it going moldy. What we use for food irradiation is either cobalt-60 or cesium-137 with gamma rays. They've also irradiated milk, and we're able to leave it on the shelf now. Gosner, I think, has some that are just on the shelf, and you can go buy them off the shelf. They last for about 3 months without being refrigerated. Okay, of course, to drink it, you want to refrigerate it, right? But to be storage, it works real well. It's also been approved for meats and eggs so that they won't go bad. Okay, so artificial elements. Here we've got one that can be made, and that's supposed to be uranium, not nitrogen. That makes me laugh. Okay, that's supposed to be uranium. I can make californium. Okay, these are made by induced reactions in a particle accelerator. Lots and lots of cash involved. Oh, that means I can make gold. Yeah, you can make gold, but to make a couple grams of gold would take gold the size of this room to pay for. So yeah, I can make gold, but I'd be using a lot more gold to make it, a lot more money. Okay. All right, so this is the Hadron Collider in Europe. It's the largest and the highest energy particle. It's 17 miles in circumference, and it's located in a CERN facility near Geneva, Switzerland. It's actually way below ground, and they have to get it about 0 degrees Kelvin, as close as they can get it. It takes the energy from all the surrounding countries to run this. So they usually only run it at night, and when they run it, they run as many as they can. What they do is they accelerate up the particles and they smash them into each other to try and make new particles. And there's been several new things. If you search the internet on CERN, there's several new particles they've actually come up with. And they think they found the God particle. So that's pretty cool. It's a Higgs-Boson particle, which they think everything is made from. Well, they thought that with protons and neutrons, and now we've gone into murons and keep going down and down. So this is sort of what the inside looks like. It's tons and tons and tons of technology down there. Major, major. Okay, this is a Fermi lab, particle accelerator, and here's the Higgs particle. Again, another picture of it called the God particle. It's in Chicago. And they do basically the same thing. I did this over here so you can sort of see what's going on. They have these accelerators that they're accelerating up the particles, and then they just open it up and cross the paths so they can crash. We also have the LINC, however you want to say it, in California. In Stanford, it's a linear accelerator. So they start the particles, bring them out here, accelerate them, and smash them together. Yes?
If something goes wrong with these, what will happen?
Well, that's the problem. We're worried about dark matter. We're worried about, there was a couple books came out, a series about dark matter and how if the Hadron Collider before it came on actually went wrong, it would start a black hole in the Earth and we'd all be sucked in. All theories, we don't know, and that's the end. Okay, so what I want to do, that brings you right into physics.
Remember that accident with the super collider?
I don't.
That's why I was really fast.
Yeah, awesome. Okay. Would you get out your daily work? I'm going to do the first two with you for today. Daily work, we're looking at day 4, half-life problems. Okay. That's Mr. Banks, if you don't know him. He is a physics teacher here. And if you haven't had physics, you probably need to do it before you leave high school. Okay. So let's look at this. There's actually 2 problems here that are smashed together. So that's why I want to make sure we do them together. So underneath this, do me a favor and just take your pen and divide that amount in half so you can use half of it for 15 and half of it for 16. Okay, so what we're going to do is, and with all things like this, the best thing to do is to go through, because it's in words, and identify what you have, just like we've been doing with the gas laws. So you begin with this. What is this? What would I label that? AI, what I start with initially, amount initial, right? Of carbon-14. If the half-life, T1/2 is equal to that. How much carbon-14 remains after, look, the total amount of time. That's T. Okay, what equation do I need to use first? What do I need to find out first? The number of half-lives. So I'm going to take 28650 years and divide it by 5730 years. And somebody that's got a calculator, since I got all mine locked up and I can't get to them, please plug it in. Let's see what we get. 5, exactly. Awesome. So we have 5 half-lives. That means I can go right to this equation right here and take my initial amount, 256, divide it by 2 to the 5th power, and get an answer. Now, on your calculator, if you don't know what 2 to the 5th power is, or you don't know how to put it in, 2 5 times, okay, times the other 5 times, and I'll give you 2 to the 5th. Make sure you put it on the bottom. We got 8 exactly. 8.00, since I've got 3 sig figs, grams, and that's my answer for that one. Okay, number 16 says 1/8. Okay, 1/8 of the original amount of radioactivity sample remains. So that means I started, I'm going to rearrange this, started with 1, and now I only have 1/8. How many half-lives have passed? So I can do this in my head, or I can do it on paper. That means I went from 1 to a half, that was 1. Then I went to a 4th, that was 2. Then I went to an 1/8, and that was 3. See how I did that? Okay. You can also say 2 to what power equals 8? 2 times 2 times 2. Okay, 3. All right, so now for the rest of the period, what you're going to do is you're going to grab out your lab. So the rest of this paper shouldn't be that hard to fill out, I'm hoping, for your work. But grab out your lab in front of you. I'm going to explain it, and hopefully I explain it a little bit better than I did last period because they asked me lots of questions. Okay, so you're going to come up and you're going to get a cup of Skittles or M&Ms. Okay, you're going to get 2 napkins. You're going to go back to your desk, hopefully after picking up some colored pencils. These are my pencils, believe it or not, those are pencils. Okay, you can also dump off your brown pencil back at the back and put in your file, your quiz. Okay, when I get back to my area, I am going to open up the napkins. So I have 2 napkins that have now been opened up, and onto them I am going to dump my Skittles or M&M onto one of them. Okay, spread them out. Count how many I have. On the right-hand side of your lab, there's a data table. The 0 trial is how many total do I have. As long as you don't drop any on the floor, it will be the same all the way across. If you drop some on the floor, then you will have a difference at the first. Okay, on those tables, there's trial 1, 2, and 3. Pick 3 different colors for trial 1, 2, and 3 and color the top of them because you're going to put them on a graph in that color. A good choice not to choose would be white or yellow because they're really hard to see on the graph. Okay, so you choose 3 different colors. Once you get these counted, okay, trial 1 is how many are still M or S up. And you're going to pick those up and you're going to put them back into your empty cup if they have M or S up. Okay, the rest you're going to leave on that paper. And then you're going to dump this onto your other napkin. And the reason why I do that is because you probably only have about half of it left, and it's easier to move less than half than it is more than half. Does that make sense? So then you're going to count again how many M or S, and you're going to put them back in your cup. And then you're going to move the ones that weren't back over here. And you're going to dump it on this paper again until you get down to 0. Now, there are 33 trials on there. I might not use all 33. That's okay. Once I get done and I have none left with M or S up, I put them all back into the cup and I do trial 2, starting at the beginning again. Then I do it again and do trial 3. Once I get all of the trials done, I can eat the M&Ms or Skittles because now they're radioactive free. Okay? And then just finish up the lab and work on your assignments. Okay? So questions, do trial 1 first all the way down till you have 0 S or M up. Then put them all back in the cup, do them all again till 0 M or S up. Okay? So those colors then you're going to take on the other side, flip over the page. On the back side, there is a place for a graph. You're going to use that place for a graph, and along the bottom, you're going to put the most trials it took to get to 0 on any of them. And then you're going to put how many at the very top you had total and work down. So make the graph as big as you can on there. And you're going to put all 3 trials on the same graph, different colors.
They'll all be exponential.
They all should be exponential graphs. Okay? All right, move. Let's go.